Okay, so in Chapter 4, we're going to review some basic trigonometry. If you have any questions about what we go over in this section, you should read the chapter in its entirety, because sections 4.1 through 4.5 are meant to be review. So we're going to skip around a little and start in section 4.2, talking about right triangle trigonometry. And so in this figure here, what we're trying to do is describe the angles as ratios of the corresponding sides of a right triangle. And that's where the word trigonometry comes from, the study of three-sided figures. So if you take a look at the diagram, we have a right triangle, where right here angle C is a right triangle, and I'm going to call angle A theta to try and review how we can describe theta in terms of its 6 trigonometric functions. So sine of theta is the ratio of the opposite side to the hypotenuse. So if you remember, the hypotenuse is always across from the right angle. And so letting theta be angle A, the ratio of the opposite side to the hypotenuse would be A over C. Cosine theta is the relationship between the adjacent side and the hypotenuse. So using this diagram here, that would be the ratio B over C. And tangent theta is the ratio of the opposite side to the adjacent side. So in this diagram, it would be A over B. There's 3 other trigonometric functions, and we sometimes call them the reciprocal functions. And that's because they are the reciprocal fraction to sine, cosine, and tangent. So cosecant theta would just be C over A, the reciprocal of A over C. Secant theta would be C over B, the reciprocal of B over C. And cotangent theta would be B over A. Now, angle A and angle B would have different trigonometric functions if that's what we were calling theta. And perhaps you remember the moniker SOHCAHTOA can help you remember those 3 relationships. Okay, so we're going to be working with 2 special triangles a lot. The first special triangle is the 45, 45, 90 degree triangle. And you can, of course, memorize the trig functions for 45 degrees and 90 degrees, but it's sometimes easier to understand where it comes from, because then if you forget what you've memorized, you can just recreate a triangle on your scratch paper and kind of come up with the trig functions. So if we have a 45, 45, 90 degree triangle, then we have 2 congruent angles, which means the sides opposite them are also equal. So this is also an isosceles triangle. And so what I'd like to do is see if I can write the hypotenuse as a function of the sides A, and then see if I can find the rules for the sine, cosine, and tangent ratios in this triangle. So using the Pythagorean theorem, I have a squared plus a squared equals h squared, or 2a squared equals h squared. So if I take the square root of both sides, then I can see that the hypotenuse is equal to the square root of 2a. So I'm going to put that on my diagram. Now I've highlighted here the top angle 45 because I want to see if I can describe the sine of 45 degrees using this right triangle. So opposite of sine 45 is a, and the hypotenuse is square root of 2a. So if I reduce that, I get 1 over the square root of 2. And if I rationalize the denominator, then I see that the sine of 45 is equal to the square root of 2 over 2, regardless of what a is. A could be anything. And then I can do the same for cosine of 45 degrees. So adjacent to 45 is a. The hypotenuse is square root of 2a. So similarly, the a's cancel. And after I rationalize the denominator, I get the square root of 2 over 2. So sine 45 degrees and cosine 45 degrees are the same. So lastly, tangent 45 is the opposite over the adjacent, or 1. So you can memorize these 3 facts, or you can just sketch this little triangle and get it the same way. Another special triangle comes from taking an equilateral triangle and cutting it down the middle and forming a 30, 60, 90 degree triangle. So we're going to take a look at the left-hand side that I've highlighted here, but imagine that we started with an equilateral triangle and all 3 sides were to us. So if I cut one of the 60 degree angles in half, then I create a 30 degree angle and a 30 degree angle, And then that also cuts the bottom base in half, so I have side length S and S for a total of 2S along the bottom. So let's start with seeing if we can write this H again in terms of S using the triangle on the left I've created there. So using the Pythagorean theorem, I would have S squared plus H squared equals 2S squared. And if I solve for H squared, that would give me H squared equals 4S squared, sorry about that, minus S squared, or H squared equals 3S squared, or H is equal to the square root of 3S. So let's take a look at 30 degrees first and see if we can find sine of 30 degrees. So sine of 30 degrees is opposite over hypotenuse, or S over 2S, which reduces to 1/2. Cosine of 30 degrees is adjacent over hypotenuse, so we just said the adjacent side was the square root of 3S over 2S. The s's cancel, and I get the square root of 3 over 2. And tangent of 30 degrees is the opposite side over the adjacent, or S over square root of 3S, which reduces to 1 over square root of 3, or if I rationalize that, square root of 3 over 3. So we can do the same thing for 60 degrees, but I'll let you go ahead and do that on your own, because in your note packet is the list of all of the trigonometric functions for these basic 30, 60, 90, and 45, 45, 90. So you can try the same exercise and confirm on your handout that you got the correct measures.